Okay, in this video I'm going to talk about energy level diagrams and Lewis structures, and I'm going to show how they sort of relate to each other and how understanding the energy level diagram for an atom can help us show what's going on with the bonding. So if I start with zinc, whose atomic number is 30, and fluorine, whose atomic number would be 9, and they're going to form a ionic bond here, which means zinc, I don't know what I'm doing there, zinc would have 2 valence electrons in the first place, and fluorine would have 7 valence electrons and a very high electronegativity. So these electrons would transfer from the zinc to the fluorine. We would require 2 fluorines to take the 2 electrons from the zinc. And so we would end up with the Lewis structure, zinc 2 plus, and fluorine minus 1 each, 2 of them. Okay, so that's the ionic bond that would form. Now let's see what this looks like from an energy level diagram perspective. So for 30, we're going to go 1s, 2s, 2p. I'm just going really fast here because these are all inner and we're not that interested in them. 3s, 3p, 4s, 3d. Okay. 2 here, 6 more here, 2 here, and then the d's. 1, 2, 3, 4, 5. Okay, now 2, 4, 10, 12, 18, 20. So I got 10 more to go. So when forming this chemical bond, when fluorine comes around, despite the fact that these are higher energy level electrons, these are the 2 outermost electrons. So these are the 2 electrons that it would lose in forming these ionic bonds. And then fluorine would have space to take 1 of those electrons. And then we need a secondary fluorine to take the secondary transferred electron. And so we can see from these holes that fluorine is ready to receive electrons, and we can see that if we empty this shell, now all these shells are full, why zinc is able to give up 2. We also can realize why zinc wouldn't be multivalent in this case, because these 3d shell is already full, so it's not going to give up any more electrons, or it's not going to promote any electrons to that 4s level, so that it could give up more, even for a strong atom like fluorine. So we can see the energy level diagram showed us where the electrons go and where they come from to help us understand the transfer of those electrons. Now let's look at the same thing, but with a covalent bond. Here we're going to have carbon, and it's going to form 4 bonds with hydrogen. Okay, so our carbon, which has an atomic number of 6, has an energy level diagram like this. And it's ground state, so it has 1s2, 2s2, and 2p, 2 electrons. Now what we can see in this situation is that it wants to form 1, 2, 3, 4 covalent bonds, but it seems to only have electrons available to share for 2 of those bonds. So something must happen here, a promotion process for one of its electrons that allows it to go into a state where it can share electrons with 4 hydrogen atoms. The process that's going to happen here is something we call hybridization. 2 things happen in hybridization. 1, the electrons are promoted for sharing, and this may happen or may not happen depending on what's required for the bonds that are required. And the second thing that is going to happen is the orbits are going to take on a new shape. every bonded orbit has to be the exact same as all the other bonded orbits. And so we can't have p-shaped orbitals and s-shaped orbitals. So something funny happens where we form a new kind of orbital that we call an sp3 orbital. So the 1s electrons are left alone. The 2s electrons, one of them gets promoted, and then the orbitals hybridize, which is instead of thinking themselves as one s orbital and 3 p orbitals, they become sp3 orbitals. And there are 4 of those, 1, 2, 3, 4. And then we get 1 electron in each one of those sp3 orbitals. Hydrogen can then come along and share its 1 electron with each one of these. And so we get 1 carbon sharing pairs of electrons with 4 hydrogen atoms. So this is our very basic introduction to hybridization. We're going to see more situations of hybridization as we go here, but the idea here is that we can promote electrons into unused shells so that we can have more availability for bonds. And then secondly, any single bonded orbital must change shape so that all of those bonds appear identical. And so instead of thinking of this as 1s and 3p, they hybridize, or they change shape, and they become the sp3 shape. The sp3 shape, we know, is a tetrahedral shape. So instead of these orbitals appearing as a sphere and 3 dumbbells, all in different orientations, they change into one of these sp3 orbitals. And if we think about this, we can realize that this is the configuration that lets all of these hydrogen atoms stay as far away from each other as possible, or use the space as efficiently as possible. So that's a Lewis structure, that's its energy level diagram, and that is how it hybridizes to form the actual Lewis structure. We're going to talk a lot more about hybridization and see a lot more examples of how these atoms can change into these new formations that will allow them to share electrons in the bonds that we observe.